Hi students, today we are going to learn a new chapter called Elementary Graph Algorithms. So for students taking this class, I assume that you already have some background on graph algorithms. But anyway, we are going to repeat some basic concepts and before we learn something new. Okay, so first of all, let's see what is a graph. So here are some examples of a graph. So here you have a graph looks like a triangle. And I can also add more nodes to it to make it more complex. So this is also a graph. So in the graph, we have a bunch of nodes. And these nodes also are called vertices. So each one is a vertex. Each one is a vertex. So this is the vertex, 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 vertex. So say node, node, same thing. And multiple nodes are called multiple vertices. And also here we have edges. So here every edge connects two vertices or two nodes. So that is what a graph is like. And we often use the notation for graph. For example, this graph we can call it G. We say G equals the set of vertices plus the set of edges. And then V would be the set of vertices in this graph, and E would be the set of edges in this graph. Okay. So for example, if we call these vertices A, B, C, D, E, and F, A, B, C, D, E, F, then the set of vertices here will be V equals the set, which is A, B, C, D, E, and F. Okay. And similarly, E will be a set of edges we have here. Now, how to represent an edge? There are two ways. You can represent an edge by using the parallel notices which are its endpoints. Therefore, this edge will be called CD or DC because here the edges don't have directions. So therefore, DC means this edge, a pair. You can also call it CD, it's the same thing. Okay, and alternatively, if you want, you can also give every edge a name. For example, you can call this edge X. So X will become the name of this edge. Then for this graph, E will be a set of edges we have in this graph. Okay, so I hope that's simple enough. And the example I've shown here is a special kind, it's not special, it's a graph where the edges don't have directions. So an edge is between two nodes without any direction. So this is graph that we call undirected graph. So we call this one undirected. And you can also add edges to add direction to the edges, and then you'll get something called directed graph. Okay. So what's an example of directed graph? For example, if I draw a graph like this, say nodes A, B, C, D, and I add a direction to every edge. Okay. Now, not every edge here has a direction because we added it. And for this edge, it's from A to B, so we represent by AB. And you cannot represent this edge by BA anymore because we don't have this edge from B to A, only from A to B. So here we have this edge AB. And similarly, this edge would be called BC, from D to C. And alternatively, you can also give every edge a name. For example, we can call this edge X, call this edge Y, so that's our own choice. That's fine. Okay, so here's the difference between directed and undirected edge graphs is that undirected graphs don't have direction on their edges. They are connected bidirectionally between the two nodes. And for directed graphs, we have a direction. So the importance is that if we talk about something like finding a path in a graph, then if the edges have directions, then we have to follow the direction of those edges when we take this path. Now for undirected edges, it doesn't matter because there's no direction here. Okay, so these are the two concepts called undirected and directed graphs. Now besides that, sometimes we also want to add weights to the nodes. For example, we can say maybe this node has some weight 3, this node has weight 2, this node has weight 1.1, and so on. And if we do this, then we get a graph which is called a weighted graph. Oh, we can also say the vertex weighted graph because here the vertices have weights. So it's a weighted graph where the weights are on vertices. And then similarly, you can also add weights to edges. Maybe this edge has weight 3, maybe this edge weight 1 and 2 and 5. In this case, it's a weighted graph where edges have weights, and we call it an edge-weighted graph. Okay, so this is the concept of weight. All right, now let's look at some special graphs. Say, for example, if I draw a graph like this, so what kind of graph is this? This is a path, right? This is a path. It's a path. It's a path where edges don't have directions. But if I draw add direction to these edges, then we have a directed path. And what is this? No, that's called a cycle. So here the cycle has no directions, it's an undirected cycle. But we can also add direction to the edges. Now this becomes a directed cycle. Okay, so one more thing. If I draw a bunch of nodes and add all the possible edges between them. So here we have 4 nodes, so I can have at most 6 edges. And here, all the 6 edges are here. So what do we call this? This is what we call a complete graph. A complete graph. It's a complete graph with 4 nodes and all the possible edges. So now let's see another example of a complete graph. Let's say that we have this graph. So we have 5 nodes. And then we also add all the possible edges between them. Okay, so this is called a complete graph with 5 nodes, because here we have 5 nodes and all the possible edges. 5 choose 2, which is 10 edges. Okay, so these are examples of the complete graphs. And so we know what the path is, what the cycle is, what the complete graph is. And one last thing is, let's take a look at this graph. So this is the connected graph. This is a connected graph with no cycles in it. And what do we call this? So I think you all know the answer. This one is called a tree. So this is a tree. And in this tree, if you draw the tree like this and put one node at the top and everything else below it, then people often think that the top node is called its root. It's a rooted tree node. But, so whether you want to have a root or not for the tree depends on, it's your choice. But you can always pick a node to be the root and put everything below it, so make the tree grow like this. Okay, and how do we call all these nodes which are on the edge of this tree that have degree 1, that has only one neighbor? So these are called leaves. So each node here is called a leaf. Each node is called a leaf here. And for those nodes which are not leaves, we call them internal nodes. Internal node. Okay, so leaves are the nodes which have degree 1. They are on the edge of this tree, and everything else is called an internal node. Okay. Now, if for a rooted tree, for 2 nodes which are next to each other, what do we call them? They are called siblings. So for 2 nodes which are next to each other, side by side, they are called siblings. And the node above them is called their parent. So that's the parent node, and it has 2 children, and these 2 children are siblings. And for this node, it has 3 nodes. So let's call this one A, and let's call this one X, Y, and Z. So here, node A has 3 children, X, Y, and Z, and the X, Y, Z are siblings of each other. Okay, so this node A is not only a parent of X, Y, Z. We also call A is an ancestor of X, Y, Z, and actually any node above it are all ancestors of X, Y, Z. So basically, if for every node, when you go up towards the root, every node you meet on the way up to all the way to the root are called your ancestors. And similarly, if for any node that's below it, then that's called That's called descendants. Okay, so assume that these are all the concepts that you already know about, and I just want to give a quick review of what the basic concept in graph theory. And now let's turn to what we're going to learn from this chapter. The first thing we're going to learn is called the representation of graphs. So how do we represent a graph using some data structure? So it sounds like a simple question, but actually it matters, because when we try to solve a problem, a graph problem using some algorithm, one question is, how is this graph represented? That will tell us how to access information in this tree, in this graph. And also, the way we represent the graph will determine how many bits this graph will take. And that is basically input size for this problem. And we know the complexity is measured as a function of the input size. So knowing input size is also important. All right. And one more word, why are graphs useful? Actually, graphs are very useful for many algorithms because graphs represent some simple and fundamental data structure. So nodes and edges. Here you can have nodes which represent different kinds of objects, and edges between nodes represent their connections. For example, if you have a social network, then every node may be a person, and if two people are friends with each other, then there's a link between them, so you have a graph. And as another example, you may have the internet, where every computer is a node, and if two computers can talk to each other directly, then you have a graph, because the connection between nodes become the links or the edges. And if you are in digital design, then you can see a circuit as a graph, where every device is the node, and if they are connected, if two devices, maybe every basically component is a graph, and if you have two transistors which are connected to each other through a link, through a wire, then we have an edge between them. So graphs is a really fundamental and a versatile representation of many things. That's why graph algorithms are very used very often. It's prevalent. Okay, so now let's talk about the first question we want to study, which is how to represent graphs. So we have basically two methods. One is called adjacency list. And the other one is called adjacency matrix. So they are quite straightforward concepts, so let me just illustrate what they are using an example. So let's say that we have a graph that looks like this. Okay, so let's say that this is our graph with 5 nodes and a set of edges. So in the adjacent list, what we do is, for every node, we record what are its neighbors. So here's the solution for adjacent list. So in adjacent list, for every node in the graph, we remember what are its neighbors. And if it's an undirect graph, then the neighbors is quite clear. But if it's direct graph, then you can remember what are the neighbors following my outgoing edges. So it works for both undirect and direct graphs. Okay, so for this graph, for node 1, what are the neighbors? Well, node 1 is connected to node 2 and node 3. So you can say node 2 and 3 are its neighbors, right? And for node 2, what are the neighbors? For node 2 has neighbors 1, 3, 4, 5. So 1, 3, and 4, and 5. Now for node 3, how many neighbors does node 3 have? Node 3 has neighbors 1, 2, and 4. So it's 1, 2, and 4. And for node 4 has 3 neighbors, 2, 3, and 5. Okay, the 3 to 5, the order does not really matter. So for node 4, it has neighbors 3, 2, 5. 3, 2, and 5. And what about node 5? So how many neighbors does node 5 have? Node 5 has just 2 neighbors, 2 and 4. Okay, So 2 and 4. All right. So this way, we have remembered all the edges and all the nodes in this graph. So you can see that what we have on the left-hand side, this column, we have all the nodes. And then for every node, we remembered what are its neighboring nodes. Essentially, we're remembering what edges it has. So we have also recorded all the edges. Okay, so now let's think about it. Say that we have a graph. Say we have a graph like this, which is called G, with a set of vertices and a set of edges. So with this representation called adjacent list, so how many, let's say, how much data do we need to record this adjacent list? Well, let's take a look. First of all, we need to record all the vertices. We have one entry for each vertex, and therefore the size here is order of v. Right? We need to use v numbers to remember these v nodes. And what about the edges here? How many edges are we remembering? How many numbers do we need? So actually, every edge is remembered twice, because for every node, we remember what neighbor is. For node 1, it has a neighbor 2, and it has neighbor 3. Right? 2 and 3. And then later, when we talk about the neighbors of node 2, we count this edge one more time. Because for node 2, it has neighbor 1, 3, 4, and 5. So you see for node 2, it has neighbor 1. So every edge is counted twice. And therefore, the number of numbers we have here, recording all the edges, is totally 2 times e. 2 times e. And this is the result. This is the size of this adjacent list for undirected graph. Because in the undirected graph, every edge is counted twice. But if it's a directed graph, then the answer will be just v plus e. Because in a directed graph, every edge will be counted once. Why that? Because in a directed graph, for every node, we only remember its outgoing edges. And so every edge will be counted only once. Okay, so the answer will be v plus e. But no matter what, in both cases, we see that for the adjacent list, the size we're using is order of v plus e. Okay, the size of v plus size of e. Now, in algorithm, sometimes people use a convention that you can also just write it as order of v plus e. But what they really mean is this is size of v, this is size of e. They don't really mean to add up two sets, which won't make sense, right? Okay, so this is just a convention. So every time you see order of v plus e, you should know that what they really mean is the size of v plus the size of e. Okay, so this is what the adjacent list is. Now let's take a look at another example for adjacent matrix. Okay, so actually we can, let's just modify this graph a little bit to get a direct graph. Now for this adjacent matrix representation, it also works for both undirected and directed graph. But I just want to show you an example of a directed graph to see how it works. Okay, so let's say that we have a graph like this. Okay, so now we have a directed graph. So in this graph, we have 5 nodes, 1, 2, 3, 4, 5. And therefore, we are going to create a matrix which has 5 rows and 5 columns. Okay, so we are using a matrix with 5 rows and 5 columns. And so the 5 rows correspond to 5 nodes, 1, 2, 3, 4, and 5. And the 5 columns also correspond to the 5 nodes, 1, 2, 3, 4, and 5. Now here's how we put numbers into this matrix. So basically, if you look at an entry in this matrix, let's say the entry on ith row and the jth column. So if there's an edge from node I to node j, then we put a number 1 on it. But if there's no edge from node I to node j, then you put a 0 to it. Okay. So again, remember, if there's one edge from node I to node j, then on entry on ith row and j's column, the entry will be 1. Otherwise, it will be 0. Okay. So now let's see what the result will be. So here, do we have an edge from node 1 to node 1? We don't, right? So in general, we could have an edge from node 1 to node 1. That will be called a loop. But here we don't have a loop, so the entry is 0. Do we have an edge from node 1 to node 2? We do. Okay, so entry here is 1. What about node 1 to node 3? So we don't have an edge from node 1 to node 3. We only have the edge in the reverse direction, and that's a different edge. So from 1, 3, it's a 0. What about 1, 4? There's no edge from node 1 to node 4. It's a 0. What about 1, 5? No edge. Okay. Because node 1 has only one outgoing edge, so you only have 1, 1 in this row. All right, so let's take a look at node 2 now. How many outgoing edges does node 2 have? So node 2 reaches node 3 through an outgoing edge. Node 2 can reach node 5, so it's 2 and 5. So node 2 cannot reach 3 and 5, so it's 2 to 3 is 1, 2 to 5 is 1, 3 and 5. And then all the other entries we have zeros. And for node 3 can reach node 1 and node 4, but not node 2, right? Because that edge is an incoming edge. So node 1 and node 4. So 1 and 4, and everything else is 0. Now for node 4. Node 4 can reach node 5 and node 2. So node 2 and node 5, 2 and 5. And everything else is 0. Now for node 5 has no outgoing edge. So therefore here, all the entries will be zeros. Okay, so this is what we have. This is what we call an adjacent matrix. And it's, again, adjacent matrix is a binary matrix which has v rows and v columns. So here v is the number of vertices. And each row corresponds to a vertex, each column corresponds to a vertex. And if a node I can reach node j through an outgoing edge, then on ith row and j's column, that entry will be a 1. Otherwise, it's 0. All right. So another question is, we have this is what we call adjacency matrix. Okay. So let's ask the question: for adjacent matrix, how many numbers do I have to represent this matrix? And that is quite easy, right? Here, because basically the size will be v squared. Okay. And in other words, we also say size is the order of v squared. Order v squared. Okay. So therefore, in terms of if you look at the order, so for the adjacent list, it's the order of v plus e. For adjacent matrix, the order is v squared. Which one is bigger, which one is smaller? Well, that depends on how large e is. Because the size of e can really be as small as 0, and it can be as large as v squared, if we allow cell groups. So therefore, if e is of the order v squared, then the two become the same order of size. And if e is less than order v squared, then this one seems to be smaller, right? Okay, but this is we say that we are doing this comparison, assuming that the numbers are just numbers. We don't consider how many bits are used in each number. So if we consider how many bits are used in each number, then there's a subtle difference again, which I think you can all figure out. So basically, if you think about the adjacent list, every number in it is an index for a vertex. So actually, if you talk about the bits, then here, since you have v vertices, how many bits do you need at least to represent each vertex? You need a log of v bits, right? And for adjacent matrix, every bit is a real bit. It's either 1 or 0. Okay. So in that sense, I would say, if we really count the number of bits we need, then for adjacent matrix, it's really v squared bits. But for adjacent list, you may say that it's actually as large as not order v plus e, but order of v plus e, order v plus e times another factor, which is the log of v. order of v plus e times log of v, because here we count, if we count the number of bits, then the index for each vertex should be at least the log of v bits. Okay, so we have an extra factor here. But anyway, you got this idea. Okay, now, so this is just comparing the size of these two representations. But size is not the only thing. What about convenience? So if we use the two data structures for algorithm design, so which one is more convenient? And that actually depends on how you want to use it. For example, for adjacent list, if your algorithm needs ask this kind of question, so if your algorithm often asks, given a vertex, what are the neighboring nodes? Then in that case, adjacent list will be very convenient because it already gives you a list. For every node, you know what the list of neighbors are. And for adjacent matrix, if your algorithm asks this question, so between two nodes I and j, is there an edge between them or not? So for this kind of question, adjacent matrix is really convenient because the answer is right there. You just check the node, check the entry in the ith row and j's column to see if it's 1 or 0. Okay, so these two data structures both have their own applications. And which one do you want to choose? It depends on which algorithm you want to design. So it's your own choice. Okay, so therefore these are the basic representations for graphs. And when we design an algorithm, we can always decide which one to choose. And often we don't always say it, but if you really want to specify details of the algorithm, then you may want to mention which data structure you are using. But often people don't mention it because this is such a basic thing. So based on a person's algorithm, we can often see right away which data structure is more convenient. Okay, so this is all we want to say about data representation for graphs. So now let's move on to the next topic called graph search. Okay, we have a breadth search, and people often call it BFS because here you have B, F, and S. So this one is called a BFS, breadth search. So what is a breadth search? Basically, breadth search is a way to search all the nodes in a graph to understand how the nodes are connected to each other. And breadth search often is used as a procedure in the algorithm. It's actually used quite often. So I think for students who are taking this class, many of you probably have already learned about breadth search in some previous classes. But today we're going to introduce it again, and hopefully you'll see something new. That's my hope. Okay, so breadth search. So what is breadth search? Let me first give you some intuition. Say that you have a graph. You have a graph where then you can start with some node. This is your starting point. And you want to understand what are other nodes in this graph, and this is how the breadth search works. First of all, it checks all its neighbors to find out what its neighbors are. And then from every neighbor, it checks its neighbors. Okay, you try to discover more nodes by looking at the neighbors. So this way, you have not only found out all those nodes which are 1 hop away, you have also found out all the nodes which are 2 hops away. And for every node which is 2 hops away, you again look at its neighbors to see what other new nodes you can discover. So this way, you can discover all the nodes which are 3 hops away from this root node, the node that you began with. And you keep going until you cannot reach any new node anymore. So this is how breadth search works. And it works for both directed and undirected graphs. Okay. So I think the idea is quite clear, right? You start with one node, then first you check all the neighboring nodes. And these are nodes which are 1 hop away. And from these neighboring nodes, again you check their neighbors, and then you get all the nodes which are 2 hops away. And after you have found all the nodes which are 2 hops away, you check their neighbors, then you found all nodes which are 3 hops away from the root node, and so on. So it's like flooding procedure. You gradually reach all the nodes based on how, and in the order of how far away, how many hops away they are from the root. So that is breadth search. Okay, so let's take a look at a small example to understand better how it works. Okay, let's say that we have this graph. Okay, so in this graph, let's give them a name. Let's say this node is A, node B, node C, node D, so E, F, G, H, I, J, K, L, M, and N. So this is the graph we have. And then what kind of graph is this? Right, it's a tree. Okay, so let's say that we are going to run BFS on this tree, and we start with the root node, A. So at this moment, we have discovered A. And then what we do next is from A, we discover all its neighbors. Whether you have adjacent matrix or adjacent list, you can do that. And actually for BFS, having an adjacent list will be really convenient. So let's assume that we have an adjacent list for this graph. So given node A, we can check its adjacent list entry and find out that its neighbors are B, C, D. So from A, we get B, C, and D, right? So from A, we discover B, from A, we discover C, from A, we discover D. So these are nodes which are 1 hop away. And then we check the nodes which are 1 hop away from A, one by one. So first we come to B. From B, we ask, what are your neighbors? And we found E, we found F. So they are 2 hops away. And next, we come to another node which is 1 hop away to see what are your neighbors. And we get G. And then from D, we get its neighbors. So we found, we are missing one here. Let's call them X. So X, H, and I. And then we look at all the nodes which are 2 hops away and check their neighbors in order to get all nodes which are 3 hops away from the root. So we come here, we come to G. From G, we discover I, J, JKL. And then we come to the next node which is 2 hops away, X. We discover M and N. Okay. So we are discovering these nodes layer by layer based on how far away they are from the root. And we discover all the nodes. So this is BFS. Is that simple enough? It's very intuitive, right? All right, so this is BFS. So now let me tell you a little bit more about BFS. When we run BFS this way, we are not only discovering all the nodes that A can reach, that this root node can reach in this graph. We are also finding out how far away every node is from the root. In other words, we're actually finding the shortest path from the root node to every node else. And at the same time, we not only find out how far away, we also find out the shortest path from the root node to everything else, to every other node. And that's what we call a tree called a breadth search, BFS tree, and which is also called the shortest path tree. So let's use another example to see exactly how it works. So this example is kind of trivial because it's a tree itself. So the BFS tree is just the original tree. So it's not very obvious what's happening. But let's use another graph to show how it works. And this will be a more complete presentation of this BFS algorithm. Okay, so let's take a look at this graph. Say that we have a graph with 8 nodes. Node R, node S, node T, and node U. And also node V, node X, node Y, and node Z. Okay, so we have a graph with 8 nodes. And this is how they are connected. So this is the graph. It's an undirected graph. All right. So now what we're going to do is we're going to run BFS on this graph to find out how far away every node is from a root, and also how they're connected to the root through shortest path. And all this can be done with a BFS search. Okay, so let me explain a little something to you first. So we're going to use some terms for every node. Every node will go through 3 stages. In the first stage, it's called undiscovered. So before you see a node, we see that this node is undiscovered. And at some point, you are going to discover a node, but then you have not really checked out all its neighbors yet. And if that's the case, then we'll say the node will become discovered. Discovered, but not finished. And if you have not only discovered a node, but also you have checked out all its neighbors, then we say that node is finished. So every node will go through these 3 stages. Initially, it's undiscovered. And then at some point, it will become discovered. And later, after you check out its neighbors, then this node becomes finished. Okay. Okay, so this is how we call it. And so we can say that maybe the undiscovered node, we can use the white color for it. And for the discovered node, we can use the gray color for it. And for the finished node, we can use the, say, black color for it. Okay, 3 colors. And also, for every node, we are going to remember 2 things. For every node, remember 2 things. Number 1, how far away it is from the root. So for every node, for each node, we remember for each node V, we are going to remember the distance from root to V. And here distance, here the root is the node that we started with. So for every node, we have to remember how far away is the minimum distance from the root to this node V. And we are going to call this one a D of V. Okay, D of V. And the second, we are also going to remember how did we reach node V from the root. So which node discovered V first? In other words, if you look at the shortest path from the root node to V, where does this path come from? So which node discovered V? And that's what we'll call let's say the pi of V. The node that discovered V. Okay, so the node that discovered V, and we are going to call this one pi of V. Okay, so every node has 2 numbers. One is how far away it is from the root. Second is the path from the root to the node V, which node does it pass through before it reaching V. And we call this one pi of V. Okay, so now let's run this BFS algorithm and see how it works. Alright, so let's take a look at this graph and see, let's pick a node to be our root node. So how about we pick node S? Okay. Alright, so let's pick this node S to be our root node. And we are going to use a data structure called a queue to remember the nodes that we have discovered. So we're going to use a data structure. This is for remembering the discovered nodes. Okay, so let's do this. we're going to use a Q to remember all the discovered nodes. Okay. And initially, we pick this node S as our root. So initially, this node S becomes discovered. So this is S, right? In this Q, we have S now. So S is discovered, and every node else is still undiscovered. So S is only discovered node. And so we have a D of S equals 0. So this is quite obvious because the distance from S to S is 0. There's no path. Okay. And also, the pi of S is just nil. So this is just by default, right? From S to S, you don't need any path. So there's no predecessor on this path. Okay, so now let's do this. From S, let's discover all its neighbors. So from S, we can discover T. So T enters the Q. And from S, we discover X. X is also a neighbor, so we put X into the Q. And now that we have discovered S, the S neighbors, S becomes finished, right? It's becomes finished. So therefore, we can remove the S from the Q now, because S is not finished. It's no longer a discovered node, it's a finished node. But the T and X have been discovered. So T and X are now discovered nodes, and they are put in the Q. Okay, so what about the parameters for them? So because S discovered these two nodes, and D of S is 0, so therefore T and X are both one hop away from S. So D of T equals 1, and the D of X also equals 1. And the pi of T equals S, and the pi of X also equals S, because for both of them, S discovered them, so they came from S. Okay. Okay, so now we're done with all the neighbors of S. We have discovered all the neighbors of S. Now let's take a look at this Q again, and so we look at the first element in the Q. So you know, a Q is the first in, first out data structure. And right now, T is in the front, so let's read T. We take a look at T. Oh, I'm sorry. So this node is actually not T, it's R. So I should say this is the D of R equals 1, and this is pi of R equals S, right? My apology. Okay, and also here we have R and X. Okay, so now let's take a look at this Q and see what is the first element. It's R. So for R, let's check its neighbors. So R has only one new neighbor, which is V. Okay, so let's put V into the Q. So from R, we discovered V. So now V is in the Q. And so now we are done with R. So R is now finished, no longer discovered, it's finished. So you can get rid of it. Okay, and because we discovered the V from R, we know that this D of V should be D of R plus 1. So right, R is one hop away from S, so V should be two hops away. So therefore we have D of V equals 2. 1 plus 1 is 2. And also pi of V equals R, because R discovered V. So R is a predecessor of V on the path from S to V. Okay, so now V is the Q. And now let's keep going. Let's take a look at the next node, actually the first node in this Q, and it's X. So from X, what are the nodes X can discover? Well, X can discover two nodes, two neighbors, T and Y, right? T and Y. So let's put T and Y into the Q. So now T and Y become discovered, and X is now finished, so we get rid of X. Okay, so and how far away are T and Y from S? That's rather easy, because X is one hop away from S, so T and Y are two hops away from S. So now we have D of T equals 2, and the pi of T equals X. And similarly, here we have a D of Y equals 2, 1 plus 1 is 2, and the pi of Y equals X. Okay, so let's keep going. Now the first node in the Q is V. So V. So okay, so For V, we check its neighbors to see can we discover anything new or not. And the V has no new neighbors, so therefore we are done. So for V is finished, so we get rid of it from the queue. Okay, now the first node in the queue is T. So from T, let's try to find some new neighbors. From T, you can discover this neighbor called U. Okay, so we put the U into the queue. So from T, can you discover Y? And we cannot, because Y is already discovered. And you can only discover every node once. Otherwise, it will be called rediscovered, right? But we are talking about discovering new nodes. So from T, you can discover a new node called U, and that's it. So now T becomes finished. And T discovered U, and therefore pi of U is T, that's the predecessor, and the D of U equals 3. U is 3 hops away from the root, because T is 2 hops away from the root. Okay, now let's keep going. The first node in the queue is now Y. Okay, so let's take a look at Y. From Y, which nodes can they discover? Okay, Y has neighbor T, but this is already discovered. Y has neighbor U, which is also discovered, and Y has neighbor Z. So Z is a new node. So Y discovered Z. So we put Z into the queue. And now Y is done. So we pop it out from this queue. Okay. So now the first, okay, by the way, the D of Z should be how much? D of Y is 2 plus 1 is 3. And the pi of Z is just 1, right? It came from 1. Okay, so now the first node in the queue will be U. So let's take a look at the U. From U, can we discover any new neighbor? We cannot. So therefore, U is finished. And we get rid of U. And from U, can we discover, from next node is Z. So from Z, can we discover any new node? From Z, we cannot discover any new node. So Z is also finished. Okay, so therefore we are done. Okay, now the queue is empty, and we say that the BFS is finished. We have discovered all nodes the root node can reach. And in this process, we have found out the distance from the root node to every node else. And we also discovered where this shortest path came from, so that we have built a tree. So let's take a look to see if we did get a tree. So in this graph, we use these red edges to discover new nodes. And we have some black edges here which are checked in the BFS process, but these black edges did not help us find any new node. So we found the new nodes using these red edges. And so let's get rid of these black edges. And just take a look at these red edges. Do these red edges form a tree? Yes, they do, right? So this is what we call a BFS tree. Okay, and also let's take a look at this queue here. So I want to reproduce the queue that we used. So in this queue, first we had S, then we had R, then we had X, then we had V, then we had T, and Y, and U, and Z. So let's see how they are ordered. This node S is the only node which is 0 hop away from S. And then we have R and X, which are the only 2 nodes which are 1 hop away from the root node. So S has 2 neighbors, R and X. And then, what about V and T and Y? So these are the only nodes which are 2 hops away from the root. Right? 2 hops away, 2 hops away, 2 hops away. And the U and Z are the only 2 nodes which are 3 hops away from the root. So you have 3 hops away. So we can see that in this queue, the nodes are actually ordered based on how far away they are from the root. 0 hop, 1 hop, 2 hops, 3 hops, and so on. So therefore, this BFS did visit all the nodes based on how far away from the root. 0, 1, 2, 3. Quite interesting, right? Okay, so that's how BFS works. And if we take a look, indeed, we start with S, then 2 nodes which are 1 hop away, then 3 nodes which are 2 hops away, then 2 nodes which are 3 nodes which are 2 hops away, then 2 nodes which are 3 hops away. So it's a flooding process based on how far away they are from the root. Okay, so if you look at this tree is what we call, also not only we call it a BFS tree, but also shortest path tree. Because we claim that the distance we get for every node, D of V, is actually the distance from the root to this node. And I think it's quite easy to see why, right? Because in this BFS process, the root node first discovered all the neighbors, and the neighbors are naturally one hop away. And then from the neighbors, we discover their neighbors, so those neighbors are 2 hops away. And those neighbors cannot be 1 hop away, because otherwise we would have discovered them. So from neighbors, so for nodes which are 1 hop away from the root, the new neighbors we can discover obviously have to be 2 hops away. Then from all these nodes which are 2 hops away from the root, the new neighbors we can discover from them are nodes which are 3 hops away. So this is a very easy proof. And also the edges we're using here to discover new nodes are on the shortest path. So if you take the root node, here, and take any node in this graph, and look at the only path from the root node to that node in the BFS tree. So in the tree, between any 2 nodes, there's only 1 path. So take a look at the root node and take any other node and look at the only path in this BFS tree from the root node to that node. This path has to be a shortest path, because it's through this path that we discover the shortest distance for this node. Okay, so this path has to be the shortest path, right? So this is how we prove that this tree is also a shortest path tree, in the sense that for this tree here, the path from the root node to any other node has to be the shortest path in the original graph, not only in this tree, but in the original graph. All right, so that's a very interesting property. And the BFS is quite useful because it can help us discover not only the structure of the graph, for example, what are the nodes the root node can reach, but also it can help us build a BFS tree, which can contain the shortest path from the root to every other node. And that is quite useful. Okay, so I hope you enjoyed the lecture on BFS.